Hello everyone, welcome to video 4.5 on standing waves. So here's our data booklet reference slide, and as you'll notice it says there are no formulas and that you have to be able to derive or recall standing wave formulas. What I'm going to show you specifically throughout the second half of this video is how to solve a lot of the problems, and there will be a lot of example problems in this video, how to solve them without memorizing any kind of formula, but solving it based on an understanding. So there are no formulas and there's no box 4.5 on your data booklet. You have to understand where these formulas come from, and you have to understand how to draw the corresponding standing wave diagrams from which the equations are constructed. I will show you all of that and walk you through the steps. Okay. So we're going to start off right here. What we have is, well, really two individual waves. If you're wondering why it looks like there's three, it's because the red wave is really just what's called a superposition or sum of the green and the blue waves. Okay, so something that we notice is that the blue wave is traveling to the left and the green wave is traveling to the right. In section 4.2, we learned about traveling waves, and so the green and the blue waves are traveling waves. And in fact, they're traveling in opposite directions. Something that you can quickly observe by looking at the green and blue waves is that they have the same wavelength and they have the same amplitude. Okay, so it causes a lot of interesting effects when two waves with the same amplitude and wavelength, well, move against each other. Okay, so first things first, the fact that we have traveling waves means that they carry energy. Okay, so the blue wave is carrying energy to the left and the green wave is carrying energy to the right. Now there's something called the principle of superposition. Okay, so superposition just means, well, you put two waves on top of each other. Okay, if their crests line up, that means the overall crest is going to get even bigger. If the troughs line up, the overall trough is going to get even bigger. But if you have a crest and a trough line up, then you're essentially canceling out the effect from one with the other. So that's all the principle of superposition really says. I'll show you something on a piece of paper just to help you along with that. So I guess in the simplest way, if you have, and I won't label the axes here because I'm just trying to keep it general. If you have a wave like this and you want to add another wave that's exactly in phase, and the reason I know it's in phase is because the crests all line up, the troughs line up, and well, of course, there's the crest again. So crest, trough, crest. If you add these two waves together, so in other words, if we superimpose them, okay, we're going to get a new wave. Okay, so first things first, these parts are going to line up. Okay, so we're going to have a crest here, a trough here, and a crest here. But the idea is, since the crests are lining up, the overall sum is going to be twice as high as the original crest. Okay, and that's going to come down like this. Now the points of zero amplitude, 0 plus 0 will be 0, and the two troughs add up, so we're going to get a really negative amplitude here. And then the positive sides add up as well, so this is going up. Okay, so the new amplitude is twice as big as the original. The crests are twice as high as they were, the troughs are twice as low as they were, or high in the negative direction. Okay, so that is constructive interference. You can also call that constructive superposition. Okay, constructive interference. What about destructive interference? Well, let's say I have the same wave initially. Okay, if I want to fully cancel that out, that means I have to add a wave that is exactly half a cycle out of phase. Okay, so then instead of having a crest here, I would have a trough, and instead of having that trough, I would have a crest, and so on. Okay, so if I add these two together, well, they are perfectly out of phase. So they're exactly half a cycle out of phase. So one's crest lines up with the other's trough. And likewise, this trough lines up with this one's crest, etc. The idea is there is perfect cancellation. Here you have a small positive displacement, and exactly below it, you have a small negative displacement. Same amplitude, opposite direction. So it doesn't matter which way you look at it, you are going to have perfect cancellation. And so, well, drawing the perfect cancellation, it's actually just going to be this. It's going to be a horizontal line. So you're You're not going to see it on top of the axis there, but it's there. That's perfect destructive interference. Excuse me. Now, usually you don't just have perfect constructive or destructive interference. You have something in the middle. Usually these two waves are partially lined up, in which case you would still look at the y values that are exactly above one another for the same x value, that is. So look at the y values for the same x value and add them together. So if you have a positive and a negative, well, it's going to get smaller. If you have two positives, right, it's going to get bigger. So this is what it means to have interference or superposition. So this is actually one word. Okay, superposition just means adding the waves together. Okay, back to the slides. So that's what we're saying here. The principle of superposition yields the sum of these two identical waves that are traveling in opposite directions. So just pay attention to the waves here on the top left. Let me just click here. There we go. Okay. So as the blue wave moves left, the green wave moves right. And notice that at certain intervals in time, their crests and troughs perfectly line up. For example, now, and now, and now, and now. Okay, so of course you can keep watching that. When they do perfectly line up, and actually it's seen better over here, but let's see it here as well. Oh, let's go back here for a second. When they perfectly line up, let's look at the image on the bottom here. Notice that the crests line up perfectly, leading to a super crest. The troughs line up perfectly, leading to a super trough. And the points of zero displacement, they were originally on the equilibrium line. Well, 0 plus 0 is 0, so they didn't really change. And so we get this red wave. Okay, so the red wave represents their sum. But then the blue wave keeps moving a little bit to the left, and the green wave moves a little bit to the right. Okay, so now their peaks are not perfectly lined up. But in the general scheme of things, I mean, their crests are close to each other and their troughs are close to each other, even though they're not perfectly lined up. So they still somewhat constructively interfere. It's just not perfect constructive interference. So you have a larger crest than any of the individual crests, and you have a larger trough than any of the individual troughs. However, that's not as high as when you had perfect, lining up of the two waves. Okay, so this just keeps moving further apart. So at this point, well, the sum looks almost exactly like the contributing waves. And if we keep moving, notice that it's getting smaller, the amplitude. Right? The wavelength is staying the same, but the amplitude's getting smaller. And there you have the perfect destructive interference. The crests from one wave lining up with the trough of the other. Okay, so you have a horizontal line. Let me just do that one more time so you can see it. Okay, so lined up, moving, and watch that red curve just gets shorter and shorter until it hits 0. And of course, this will continue. So as the wave moves, it's going to get taller and then get shorter over and over and over again. Okay, so this cycle continues until you have what we see right here in red. Okay, something to note is that this red wave, it's very different than the blue and green waves. Okay, while the blue and green waves are moving left and right respectively, the red wave, it just kind of looks like it's going up and down, up and down. It just keeps flipping itself over and over. Okay. Something to notice is that the red wave is not moving left or right. And that is the very nature of what a standing wave is. For both the traveling waves, i.e. the blue and the green, or the standing wave, which is the red, the particles, the individual particles that make up the wave, whether it's in a rope or the particles in the air, those particles are vibrating up and down continuously, just like we saw in section 4.2. The only difference is energy is being propagated through space with the blue and green waves, but it's not moving anywhere with the red wave. That's why we call it a standing wave. Okay? All right, now let's discuss some important terminology associated with the standing wave. There's two really important parts. Okay, so the first thing is that, like I said on the earlier slide, the red wave is not traveling left and right like the blue and green waves do. Now these lobes, so these high and low points right here, those get smaller and then they get bigger, kind of like we can see in the animation. Now we have better words for them than lobes. Okay, so as we'll see in a second, the lobe goes by a different word. Now points on the wave where there is zero displacement, so right now where my mouse cursor is, This is a point of zero displacement. This is the next point of zero displacement right here. Okay. This is the next point of zero displacement. And this is the other point of zero displacement that we can see. Okay, so where the wave has no displacement, we call that a node, represented with the letter capital N. So here are the nodes in the diagram below. Okay, so these are the points that don't move, but the lobes move up and down. Speaking of which, let's stop calling them lobes. Let's start calling them antinodes. Okay, so the antinodes are exactly in between the nodes, and these are the locations of maximum displacement. Okay, so don't get the A for antinode confused with A for amplitude. It's different. So there are the nodes in the animation and the corresponding antinodes. Okay. All right, boundary conditions. If you're wondering when we're looking at this, where you would ever need to know this or what application it has to real life, here it is. A lot of music theory is going to show up in this section, 4.5, whether it has to do with musical instruments that involve strings like a guitar, in which case both ends of the string are fixed, or if we're dealing with something that has a pipe that is open at one end and closed on the other, something like a clarinet. Now, whenever you have a stringed instrument, generally speaking, you take that string and it gets plucked. Okay, so originally speaking, that string we say has length capital L, and that's what I'm going to be using for the rest of the video. Capital L is the length of the string. If we pluck it very lightly, we're going to get something like this. Okay, when it hits the fixed end, and this is something you haven't seen yet, but this is the first time you're going to hear it, when a certain part of a wave hits a fixed boundary, because the wave is traveling, let's say, from left to right, when it hits the fixed boundary, it reflects. Okay, now, if it comes in as a crest and it hits a fixed boundary, it reflects as a trough. If it comes in as a trough, it will reflect as a crest. Okay, so whatever it hits, it always inverts. So let me just make a note of that on the sheet so you have it as well. Okay, so when a wave, or even just a single pulse, hits a fixed boundary, in other words, it can't move, the orientation of the incoming wave inverts. Okay, so that means if it's coming in as a crest, it will invert and reflect as a trough. Okay. If it comes in as a trough, it will invert and reflect as a crest. Okay, let's go back to the slides. So this is coming in as a crest. That means it's going to reflect as a trough. Okay, so altogether, when you have the incoming wave and the reflected wave, you get something that looks like this. And really, this is the simplest pattern that we can create. And actually, this is a standing wave because this thing is just going to oscillate up and down in exactly this position. Now, looking at this, we have two nodes and one antinode. Remember that the node is the region of zero displacement. Okay, so that means it has to be at the ends where the string is fixed. The antinode is the region of maximum displacement. You can clearly see that's right in the middle. The question here is, why must there be a node at the end of the string? And really, if you just think about it quickly, the reason is because that's where the string is attached to the instrument, so it can't move. That's why it's a node. Okay, so we are going to be drawing a lot of these diagrams. In fact, for the rest of the video, solving most of these problems really just comes down to, can you draw these diagrams? And then subsequently, can you create the formulas from them, which we'll see. All right, now, what you notice here is that when you pluck it the first time, so this is the simplest pattern you can create between two fixed ends. This right here, it's either you're looking at it as one crest or you're looking at it as one trough, depending on which way you're going, left to right or right to left. Regardless, it's half a wavelength. So 1/2 of lambda is equal to L. And remember I said the capital L will always be the length of the string that we're going to use. Okay, so let's say we're going with the crest. That's half a wavelength. Okay. So if half lambda is equal to L, that means lambda equals to 2L. Based on that, what we really were trying to do here is come up with an expression for the frequency of the sound in each variation of this. Okay, so now, based on the universal wave equation, V equals F lambda, if we rearrange this for F frequency, it's going to be speed divided by wavelength. All right, so if wavelength we rewrite as 2L, then F is equal to V over 2L for a string. Now, because this is the simplest pattern we can create, in order to have one node on each end and therefore one antinode in the middle, we call that the fundamental frequency, which is given the symbol F subscript 1. It is also known as the first harmonic. For those of you that study music, you will also recognize this as a certain overtone. We will not be going over the overtones in this video. All right, before I actually show you the next diagram, I want to show you something else. The idea here is, what is the simplest pattern you can create? And then the next simplest pattern that you can create, and the next, and the next, and the next. So here what I have is I have essentially a guitar string, and it's fixed at both ends. So this is fixed at both ends. And the fact that it's fixed at both ends means that I have a node at each end. All right, so the simplest pattern that I can create is a crest, which then reflects as a trough. When I draw it by hand, I like to draw the reflection as a dashed line because, I mean, it doesn't happen simultaneously, but I mean, that's the simplest you can have. You have a node on each end, kind of like we saw in the slides, and an antinode in the middle. That's the simplest you can create. In order to figure out what the next simplest wave you can create is, look at the following. I'm going to draw a series of crests and troughs. And I'm going to draw their reflection too. And just go with me for a second. Okay, imagine we have these waves. We know that for something that's fixed on both ends, so if we want to figure out the next pattern and then the next pattern and the next one, and we could go on forever, we know that because it's fixed at both ends, I need to have a node at each end. Okay, so however many I create. So this is frequency 1, this will be frequency 2, frequency 3, and I can continue this forever. When you look at how a wave looks, what we generated first here was the wave that went from here to here, right? So from one node to the next. That's the shortest possible pattern that can be configured. Okay. The next shortest pattern that can be configured, so from here to the next node, is going to be until right here. Okay, so from start to finish, that's the next shortest possible pattern that can be created. The next shortest possible pattern that can be created goes to the next node because we need a node at each end. I can't stop it in the middle because then I'd be at an antinode. Since the ends are fixed, I need a node. Okay, so what that means is the next possible wave pattern that can be created is from here to here, right? So just those two spaces right there. So it's going to look something like this. Okay, so that's coming in. The wave is hitting a fixed boundary, so it inverts upon reflection. And it looks something like this. Okay, so incoming, reflection. But what do we have here? In the beginning, we had that, so let's call this, let me just go up a bit. Let's call this L, so the length of the string in each case is L. Okay, in the first case, we had L is equal to lambda over 2. Now in this case, we're going to have L is equal to, well, how much of a wavelength or how many wavelengths is that? I have exactly one crest and one trough, so that is exactly one wavelength. L is equal to lambda. The next possible pattern I can create starts from here, this node. That was the first harmonic, that was the second frequency, now that's going to be the third. So that's one crest, one trough, one crest. Okay, so crest, trough, crest. So drawing that here, it's going to look like this. Crest, trough, crest. And then it's going to reflect, or you could do trough, crest, trough. Same thing. So that's what it's going to look like. That's the third possible look for something that's fixed at both ends. Hence, I have a node at both ends. Now this time, watch. I have a crest, a trough, and a crest. In order to have one full wavelength, I just need a crest and a trough. So that's a full wavelength from here to here. And so that piece right here, that's just an extra half a wavelength. So my L here is 1.5 wavelengths. Although I don't like to write it like this. You do not write it with a decimal. I write it as a fraction. So L is equal to 3 lambda over 2, because 3 over 2 is 1.5. So I just wanted to show you that before we get back into the slides. So when you see these patterns, you'll understand where they come from. All right. So again, this is the next pattern. Okay, so you have a full wavelength, it reflects, and you have this sort of pattern. You have nodes, and you have your antinodes. Okay, in this case, lambda is equal to the length of the string. And this here is F2. If you want to actually come up with an expression for the frequency based on the universal wave equation, we know that frequency is the speed of sound, or the speed of the wave in this case, divided by wavelength. So, and if lambda is equal to L, then F is equal to V over L. This is the second possible configuration that can be made, so we call it F2. It doesn't get a fancy name like fundamental frequency for F1, we just call it F2. Okay, also known as the second harmonic. All right, so in this example, we had to practice sketching the third frequency, so we already did that. Okay, now the only thing is we have to come up with the formula, so we'll go back to the page and we'll figure this out. Okay, so we came up with fundamental frequency, or first harmonic, second harmonic, F2, third harmonic, F3, and so now we have to come up with the expression for the frequency. All right, so to figure out the expression for the frequency, we have to remember that we're using the universal wave equation. V is equal to F lambda. So we're looking for F here, and F is equal to V divided by lambda. So the first thing you do in this case, like we did before, you make an expression for lambda in terms of L. And once you do that, you rearrange this for lambda, because that's what's going to get plugged into this formula. So lambda is equal to 2L divided by 3. So I take that and I plug it in over here. Okay, so that means F is equal to V over 2L over 3. So now simplifying this just involves, well, whether or not you understand how to simplify fractions in math. Okay, so if I have A over B over C, I have a solid number divided by a fraction. So change that into a fraction divided by a fraction. Any whole number can be rewritten as a fraction over 1. So A over 1 over B over C. When you take a fraction and you divide by another fraction, that is equivalent to taking the top fraction and multiplying it by the reciprocal of the bottom fraction. So that becomes AC over B. Okay, so that means the 3 down here is going to come up to the top. So that's going to become 3V over 2L. All right, so that is the frequency, or this is F3. Let's go back to the slides. Okay, so another way to figure out how it looks, and this is the explanation given in the slides, you can use what I showed you on the paper, or you can use this. In the fundamental frequency, we have one node on each end, no nodes in the middle. Nodes are always evenly spaced apart, just as antinodes are. Okay, in frequency 2, we have a node at each end, and we also have one equally spaced just between them, which happens to be in the middle. Now for F3, we have the 2 nodes on the ends. Okay, so let's actually stick that node in there. So we have one node in the middle here for F2. For F3, we have the 2 nodes on the ends. Now we have 2 nodes in between, and they are also equally spaced out. Okay, so if this is easier for you to remember how to draw it, you can use this method too. And we simply fill in the wave. And we've got the reflection as well. And sure enough, we have a crest, a trough, and a crest. That's 1.5 wavelengths. So that's 3 lambda over 2. So rearranging for lambda, we will have 2L over 3. Okay, so putting that in the formula based on what you just saw me do on the sheet, 3V over 2L. Now something that isn't really officially covered, but just an interesting thing for you to notice, is the relationship between each subsequent frequency and the fundamental frequency. If you noticed, F1 is V over 2L. F2 is V over L, and F3 is 3V over 2L. I'm just going to wait here for a second and pause the video if you want. See if you can figure out a formula that will connect future frequency values with the fundamental. Hey, hopefully you had a chance to pause the video there if you didn't pause it now, but let's talk about how to get this. So frequency 1 is V over 2L. If you take that number, or this expression rather, and you multiply by 2, you get V over L. Now if you take the initial expression and you multiply by 3, you get 3V over 2L. But notice that to multiply by 3, I get F3, and multiplying F1 by 2, I get F2. So what I see is that any subsequent frequency, and actually I'll write this down as a formula, this is also not on your booklets or in your notes, because this is just an observation. The nth frequency is equal to n, so whatever harmonic it is, times the fundamental. So something to notice and observe. Okay, back to the slides. All right, so that was looking at the case where we have something fixed at both ends, okay, or closed at both ends. So that was a string. Usually we look at pipes, although we do sometimes look at strings too. Now with pipes, they're either going to be closed at one end or they're going to be open at both ends. Now just like the string had length capital L, these pipes are also going to have length capital L. Okay, so assume this is part of an instrument. Okay, the mouthpiece is over here on the left. Excuse me. Excuse me. And well, you've got another piece here on the right, so some kind of closed end where the sound wave is going to get reflected. Now, what is the shortest possible wave you can fit? Well, you might not recognize this right away, but here what we have is the incoming wave on top and the reflected wave on the bottom, or vice versa. What you have is you have something going from an antinode to a node. That specifically measures 1/4 of a wavelength. Okay, now, this is something you have to remember. Whenever you have an opening, okay, so whenever the pipe is open, you have an antinode. Whenever the pipe is closed, you have a node, the reason for which we will talk about momentarily. But for now, if this pipe has length L, the wavelength, I mean, I can clearly see it's 1/4 of a wavelength. I actually want to do this on the sheet because I don't want you just watching the animations in case that is a little confusing. Okay, so this time we have something that's open at one end. So before it was fixed at both ends, now it's open on one end. And then we will move into open at both ends. Okay, so something like this. I'm going to draw the first couple for you. Okay, now just like before, imagine you have a series of waves, and I'm just going to draw the reflection here. And really this is just here to help you understand how this is supposed to look. First things first, when you have an open end, so these are the open ends, and these are the closed ends. Closed and fixed, same idea. Usually we use the word fixed for strings, closed for pipes. Okay, so whenever you have an open end, this is automatically going to be an antinode. Okay, you have to remember that. And when you have a closed end, that's automatically a node. The reason for that, and I guess I'll say it now, but it'll come up on the slides shortly. The reason for that is because wherever the pipe is open, the air has room to move. But when the pipe is closed, the air doesn't have anywhere to move. So you got to have a node at the closed end and an antinode at the open end. So let's see what is the simplest configuration we can make inside of this pipe, such that we have an antinode here and a node here. Okay, so looking at our picture, let's find an antinode. Okay, so let's say we start right here. Okay, so that's an antinode right there. The shortest possible configuration I can have, such that I have an antinode on the left and a node on the right, is from here to here, right? And if you look at that, so what would one full wavelength be? One full wavelength would be something like this. So 1 lambda, right? Because that's one full crest and one full trough. Now, how much of a wavelength is that? Okay, so if you said 1/4, you are correct. That's a quarter wavelength. And so what that means is I have an antinode here, and I have a node here. And so, okay, so it's going to be interesting to draw because it's such a long pipe. In hindsight, I should have drawn this pipe a little bit shorter, but that's okay. So we have something like this, and this is the reflected wave. So there we go. So that's the shortest possible waveform that I can create, a quarter wavelength. So this is F1, F2, and F3. Now, the speed of sound is the same because the medium that's vibrating in each of these cases is the same. And we're also going to assume that all the pipes are made of the same material. It's in the same room, so the temperature is the same. But the idea is the speed is the same, the speed of sound anyways. Now let's see if we can figure out the speed of the particular note that's created. All right, so we have F1, that's our fundamental frequency. So using our universal wave equation, V is equal to F lambda. If we want to rearrange this for frequency, frequency is going to be V over lambda. The speed's going to be constant. The frequency is what's changing. So let's come up with an expression here. So let's call this L. So the length of the pipe is L. And in our first case, we're fitting a quarter wavelength, and that's equal to L. So here we have L equals lambda over 4. Okay. So we have V, and now we have to rewrite this in terms of lambda. So lambda is equal to 4L. So we stick 4L on the bottom. So frequency 1 is equal to V over 4L. Now the second possible pattern I can create, if I start here at my antinode, here's my first node, I can't stop here because this would be another antinode, right? I have to stop at the next node. So the next possible place I can stop is right here. Now from here to here, how much of a wavelength is that? That's 3/4 of the way. Okay, so I guess let's draw it first. So I start with an antinode here, and I end up with a node here, and I know that I also have a node somewhere over here. Okay, so I have something that looks like this. So there's a quarter, there's half, and then this reflects, so therefore it inverts. So something like that. That's the next possible pattern that we can create. Now the pipe length is still L, except this time I'm fitting 3/4 of a wavelength. So L is equal to 3 lambda over 4, or 3/4 lambda. If I rearrange this for lambda, I'm going to get 4L over 3. Okay, so why don't we call this lambda 1, lambda 1. We'll call this lambda 2, lambda 2, because it's for F1 and F2 respectively. Okay, so F2 is going to be V over lambda 2. F1 is V over lambda 1. So that's going to be V over 4L over 3. Okay, so rewriting that, that's 3V over 4L. Okay. Now F3, not the last one, but the last one we're going to look at. So we have to start off with an antinode. So if we start here, okay, so this was our first pattern, the next configuration, and the next one is going to go all the way to here. Okay, so now we have, well, a full wavelength and then 1/4 of another wavelength. It'll take some time for you to practice drawing these, but you will get the hang of it. Okay, so I have a node here. So let's say I've got 3 nodes. Okay, so I've got 1, 2, 3, and then the 1/4 wavelength. So I've got something that looks like this, and then this. Okay, so now I have 1 1/4 wavelengths. Although I don't want to call it 1 1/4, don't use mixed fractions. Use improper fractions. So L is equal to 5 lambda 3 over 4. 5 over 4 is the same as 1 1/4. Okay, so we rearrange this for lambda 3 and we get 4L over 5. We're going to use that when we calculate F3. So F3 is equal to V over lambda 3. So V over 4L over 5. So 5V over 4L. So there isn't, unfortunately, a clear formula for the frequencies here, but at least you know one for the 2 fixed ends. Okay, So this is what I was trying to get at. This is how you get the formulas based on the picture. So far we came up with formulas for when you have something fixed at both ends, okay, a string fixed at both ends of length L. We have figured out the formulas for when the string is open at one end, or closed at one end, open at one end. And this is usually when you have a pipe. Let's go back. We're also going to look at the case where you have a pipe that's open at both ends. So this slide and the next few slides are just going to go over what I've shown on the page. So I'm going to go through them a little bit faster, but feel free to pause and really go through it at your own leisure. Okay, so again, here I have an antinode here at the open end and a node at the closed end. So I have 1/4 of a wavelength. That's the smallest configuration that I could possibly make. The calculations here are exactly the ones I've shown you. Here's the next possible configuration, node here, antinode here. And the last possible configuration, well, if you just want to go to F3, of course this can continue indefinitely. So we're fitting 1 1/4 wavelengths here, and solving for F3 we get 5V over 4L, just like we saw on the paper. Okay. And we talked about why the mouthpiece is an antinode and why the closed end is a node, and that just has to do with whether or not the air can move. If you have an open end, air is moving, but at a closed end, it's reflecting. So at that point, it's not moving, it's a node. Okay, now let's talk about open-ended pipes. Okay, so let's go back to the page. All right, so we looked at closed at both ends, open at one end. Now we're going to go into open at both ends. This is the last possible case, by the way. So in case you're wondering how many more of these pictures you have to draw. Open at both ends. Okay, so I'll draw, there's 1 pipe, 2 pipes, and 3 pipes. Okay, I'm going to draw my wave again, just so I know where I'm drawing to. Once you get the hang of this, you're not going to have to draw this anymore, but you know, it can't hurt to draw it. At least you'll see how it should be drawn. So we have F1, F2, F3. Now, when you have an open end, remember you have to put an antinode. And because this is open at both ends, that means I need an antinode here and an antinode here for each of them. Okay, my first antinode is right here. So obviously it's going to look like that, but what's the shortest possible design that I can make? Well, the next piece here is a node, and then the next antinode is right here. So that inside those 2 dashed lines, that is the pattern that I need to create for my fundamental frequency. So something like this. And then that's going to reflect and invert. So it came in as a trough, so it reflects as a crest, and this piece here is going to be a trough. So there is the fundamental frequency when the pipe is open at both ends. Now once again, if we call the length of this pipe capital L, so let's come up with expressions for the wavelength in terms of L, or rather L in terms of the wavelength, which we'll switch around. So in this first case, L is equal to, well, how much of a wavelength is that? If you're having trouble seeing it, remember that a wavelength goes from here to here. So that's 1 lambda. If you look, if you break it up into quarters, that is exactly 2 of the quarters. So that's half a wavelength. So L is equal to lambda over 2. After all, you have half a crest and half a trough, right? Okay, so we'll call that L is equal to lambda 1 over 2. So therefore, lambda 1 is equal to 2L. Okay, with that in mind, F1 is equal to V over lambda 1. So that's V over 2L. Okay, next, F2. What's the next possible pattern that I can create? Well, if I start here, there's my first antinode, there's my next antinode. So from here to here, that's the next possible pattern I can create. Okay, so if I draw it, so I'm going to come down, go back up, and there I have it. So it looks something like this. Okay, again, 2 antinodes at the ends. Okay, so F2 is equal to V over lambda 2. So V over, and I need an expression for lambda 2. So if this whole thing is L, how much of a wavelength do I have? Well, I'm going from the top of a crest to the full trough, back to the top of the next crest. So at this point, I would start this cycle again. And so this here is in fact one full wavelength. So L is equal to lambda 2. So that's pretty easy. I just plug L in right there. So there's F1, F2. And finally, let's get the third harmonic. Okay, so the next possible place for the antinode is right here. So from this line to this line. Okay, so that whole image in between, you got to sketch between the ends of the pipe. All right, so here we go. So we've got 1, 2, and 3, something like that. Like I said, it'll take practice to be able to draw these, but with practice, you'll get better at it. Okay, so how many wavelengths do I have now? Well, I go from crest to crest, right? So that's one wavelength, and now I'm going from top of the crest to the start of the trough. That's a quarter. So, oh, hang on a second, no. If I do, that's one full wavelength. So that means from top of the crest to bottom of the trough, that's half. There's another half, so there's another half. Sorry guys, so that's actually 1.5 wavelengths. So L is equal to 3 lambda 3 over 2, because 3 over 2 is 1.5. So lambda 3 is 2L over 3. F3 is V over lambda 3, which is V over 2L over 3, which it turns into 3V over 2L. Now something interesting here, if you notice, the frequencies obtained when the pipe is open at both ends is the same as the frequencies obtained when the pipe is fixed at both ends. Okay, so while we don't have all the calculations here on this sheet, it was on the slides, we do have one of them, and that was F3, 3V over 2L. In fact, based on the outcomes of the frequencies, we came up with this expression, Fn is equal to n times F1, and sure enough, it's the same relationship here when you have the pipe open at both ends. So it seems to work when you have it fixed at both ends and open at both ends, but not when it's closed only at one end. Back to the slides. All right. So again, these slides are just going to go through the same thing I just went through. So feel free to look at this at your own leisure. Now, at the bottom here, it says the IBO, which is the IB organization, requires you to be able to make sketches of string and pipe harmonics, both open and closed, and find the wavelengths and the frequencies. And so this is a requirement in the Ontario curriculum as well. It's a very important requirement. So just because this bullet point here says it's for IB, it is also for ministry. All right. Distinguishing between standing and traveling waves. All right, so at the beginning we said that the green and the blue waves were traveling waves, and they were actually carrying their energies well, left and right. So what do you get when you superimpose them? You get the red wave, which is a standing wave. Now, there are quite a bit of differences between the standing and traveling waves, and there are some similarities as well. So while the traveling wave does transmit and carry energy from one location to another, a standing wave does not. Although just keep in mind, in both cases, the particles are oscillating up and down, except in one case, energy gets transferred, and the other, it doesn't. For the amplitude, notice that the amplitude of the green and the blue waves is always the same. It doesn't change, right? That is the maximum displacement from equilibrium. But for a standing wave, it changes, right? If the crests of the incoming and reflecting waves are exactly lined up, you have a very big amplitude. If they are exactly lined up 1/2 out of phase, then you have a 0 amplitude. And any other position for the blue and green waves, you have something in between. So that's what it says here. It's different. But for a traveling wave, it's always the same. Now, for both standing and traveling waves, this is something they have in common. They have the same frequency. Something that I'm going to tell you, which you should just very well remember both this year and next year, and in the future when you take physics, is the frequency of a wave is always and only determined by its source. If the source remains the same, the frequency stays the same. Wavelength. Okay, so for a standing wave, the wavelength is the same as the waves that make it up. And for the traveling wave, you just measure the distance between the crests. All right, phase. I'm not really going to worry too much about the phase because after all, the red wave is just oscillating up and down. Okay, so we're just going to say the phases are the same for the standing wave and they're different for each point along the single wavelength. Now the wave pattern for the standing wave doesn't move and the traveling wave does, and that just feeds into the first line again, that the standing wave transfers energy. The standing wave does not transfer energy, but the traveling wave does. All right. Now, this is what I meant when I said the second half of the lesson, because this is where all these fun problems are going to start. I use the word fun very loosely here. All right, but it's not too bad if you understand the concepts. It won't be too difficult to do these problems. All right, a tube is filled with water and a vibrating tuning fork is held above the open end. Actually, this is a common experiment that can be done to measure the speed of sound. Now, as the water runs out of the tap at the bottom, sound is loudest when the water level is a distance x from the top. The next loudest sound comes when the water level is at a distance y from the top. Which expression for lambda is correct? Okay, so I hope you have the slides in front of you. So we're going to go to our page here. Okay. First thing I'm going to do is sketch this. So we have a pipe that is filled with water and there's a little tap at the end where the water can drain. So initially this thing is completely full. Okay, so after some time the water drains and the whole time the tuning fork is held on top, right? So if you've never seen a tuning fork, it used to be used, now I say used to because nowadays in the music industry there are electronic versions of this, but it used to be used in the music industry and might still be today to tune pianos. Okay, so these forks, they're metal forks. It's not the fork you have in your kitchen. It looks something like this. It's got two metal prongs here. They're called tines. And when you hit it, usually with a rubber hammer, these things start vibrating. And the fact that these two tines are so close to each other, it just produces this beautiful sound. Now, these tuning forks generally have some kind of rating on them, like for example, 15 kilohertz. Okay, so that means this thing would be, well, okay, maybe 15 kilohertz is really high. Let's call it 15 hertz. So that would mean that this thing is vibrating back and forth 15 times a second. Anyways, the idea is it produces a particular pitch, a single frequency. All right, so again, this thing is fully filled with water, and we open the tap on the bottom and the water starts to drain. Meanwhile, this thing is making sound. The idea is we want to see when the reflected sound is the highest, because that's when we'll know that a standing wave has been produced. So please remember that. A loud sound is produced when a standing wave is formed. So let me write that down. A loud sound is produced when a standing wave is formed. Okay, so the first loud sound happens at distance x, so that's about here. And then the water keeps draining, and nothing until the water reaches this height down here. Okay, so this is called y in the picture. So this distance here is x, and this full distance here is y. So we have to come up with some expression for the wavelength. A lot of this, you might not know how to solve the problem right from the get-go when you read it. In fact, these problems are all so different, slightly different, that you might not know exactly where to start. The key is look at what you have, try to draw some standing waves, try to come up with expressions, and you will eventually get to your answer. Okay, notice that all of the expressions for wavelength are in terms of x and or y. So here, my first loud sound is created. So what I have to ask myself is, well, what kind of standing wave will be formed here? I know at the top of the tube, that's an open end. So I'm going to have an antinode here because it's open. And the question is, what's happening where the water surface is? Would that be considered an open end or a closed end? If you said closed, you are correct. Okay, so the water surface is a node. So it's a fixed end. Water might move very slightly, but not nearly as much as the air. Okay, so what that means is we have an antinode here and a node here. The simplest pattern and the first pattern we can create looks like this. If you were to have a node and an antinode. Okay, so there's the incoming and there's the reflected wave. The next possible pattern you could get would look something like this. So in order to have a node down here and an antinode at the top, now we're going to start creating our expressions. So here I have a quarter of a wavelength. So in my first case, I know that lambda over 4 is equal to x. And in this case, well, think about it. How much of a wavelength do I have? I have a full crest and half a trough, or vice versa. Okay, so I have 3/4 of a wavelength. So 3 lambda over 4 is equal to y. Well, how on earth do I get an expression for lambda in terms of y and x? Okay, I can isolate for lambda here and get something in terms of y. I can isolate for it here too. I can say lambda is equal to 4x, but that's not one of the options. The options are x, 2x, y minus x, and 2 times y minus x. So since I know it can't be x or 2x because it's clearly 4x based on this formula, therefore it's either C or D. That means I need some expression involving y minus x. So let's see what I get when I do y minus x. So y minus x, so y is 3 lambda over 4 minus lambda over 4. So imagine you're just doing grade 9 math, okay? You're collecting your like terms. They're clearly already collected. I have 3/4 of something and I'm subtracting a quarter of that same something. 3/4 minus 1/4 is 2/4. So 2/4 of lambda. Well, 2/4, I can break that down a bit further. That's 1/2. All right, so 1/2 lambda. So y minus x is equal to lambda over 2. So then rearranging for lambda, lambda is equal to 2 times y minus x. Okay, and that is answer D. So therefore D is the correct answer. So again, from the get-go, it's hard to see where I can get the answer for this question. So you just have to dive right in, get your hands dirty, and see what you've got. I know that standing waves are going to be formed because a loud sound is produced. I know that there has to be an antinode at the open end and the closed end has a node. So I draw my possible patterns. Next, using the information I've been given, I come up with expressions for the wavelengths. Now, based on this, I could clearly see that lambda is 4x, which doesn't match A or B. So therefore, the answer should be something in terms of y minus x, which once I do the subtraction, I find out that it's D. Okay, so again, sometimes you just have to play around with these problems. And you probably see from this question, this is the type of question that I was trying to get at the first slide. The data booklet reference that there is no formulas here because you have to derive them yourself. Okay, so let's go through this because we already talked about it. Why didn't the pitch change? This is important. So pitch is another word for frequency. So I'm just going to write that here. So just make sure that's in your notes somewhere. Pitch is frequency. Why didn't the frequency change? Because the frequency only comes from the source. And what was the source of the frequency? The tuning fork. And each tuning fork is rated. So if this tuning fork was rated at 15 Hertz, that means it's always 15 Hertz. All right, next. This drumhead set to vibrate at different resonant frequencies has black sand on it, which reveals two-dimensional standing waves. This is what is known as a Chladni plate. Chladni, Chladni plate. It's really an amazing tool used for demonstration purposes. So you have a very large surface, and underneath that surface you have a vibrating motor. Okay, and that motor can vibrate at all sorts of different frequencies. Oh, sorry guys, wrong screen. So we have this drum head here, and underneath this drum head is a vibrating motor. And generally what's done is sand is sprinkled on top. So sometimes these boards are white and black sand is sprinkled on top. Sometimes the boards are black and white salt is sprinkled on top. Either way, if you watch the video that I have, it's going to show you a black surface with white salt on top. Same idea. Okay, so but the idea is that the drum underneath can vibrate at different frequencies. And as you change the frequency, the sand starts to take different patterns. Okay, so observe. This would have been definitely much more amusing and interesting if you watched the video, but nonetheless, this would be a different frequency. Okay, so look how the sand arranges itself. This is the drum vibrating at yet a different frequency and another frequency. It's actually pretty interesting. Right, now the question is, does the sand reveal nodes or does it reveal antinodes? So let's think about this. Nodes are regions where there is zero displacement, and antinodes are regions where there is maximum displacement. Okay, so originally, before this thing is vibrating, there is black sand uniformly scattered all over this white drum. So once this thing starts vibrating though, that black sand jumps from those regions. So for example, there used to be black sand here, and here, and here, and here, and here, and any other region that is currently white. But once it starts vibrating, it jumps and collects in these well-defined regions. So where would the sand jump? The sand would jump where there's a region of maximum displacement from the wave. So that means the antinodes are the white regions, and the nodes are where the sand is, so the black regions. Now, why does the edge have to be a node? Because the drum head can't vibrate at the edge. All right, let's try this. Two particles, x and y, are situated a distance half a wavelength apart on a stationary wave of wavelength lambda. Which one of the following correctly shows the variation with time t of the displacement d sub y of particle y? So this is one moment in time. It's a stationary wave. So if the particle is, for example, here, right, so for x, it's going to want to go up. And if the particle is on y, it's half a wavelength apart, so it's down here. It's going to want to go down with time. Right? So what do we have? So A is actually half a phase or half a cycle out of phase relative to the original, and that's exactly what we want. If we compare the original graph with B, that's, let's see, that's half, no, that's a quarter. That's a quarter cycle out of phase. If we compare the original graph with D, that is, well, it could also be a quarter cycle if you go in the other direction, or 3/4 of a cycle. C is exactly the same, so it has to be A. A is exactly 180 degrees out of phase. All right. A pipe open at both ends has length L. The speed of sound in the air in the pipe is V. The frequency of vibration of the fundamental, first harmonic standing wave that can be set up in the pipe is, okay, so it's best not to memorize. In fact, most of things in physics, you can't memorize. You have to work it out. Okay, so I'm going to show you how you can work this out pretty quickly. Okay, so you have a pipe open at both ends. It's the fundamental frequency, so it's the simplest pattern you can create. And the length of the pipe is capital L. All right, now the speed of sound through the pipe is V, and I know that the speed is equal to F lambda. Since I'm trying to come up with an expression for frequency, I rearrange this formula for F, and I get V over lambda. Okay, so what is the simplest pattern that I can draw inside of this pipe if it's open at both ends? So I need an antinode here and an antinode here. The simplest pattern I can create looks like this. All right, so that there is half a wavelength. So L is equal to lambda over 2. Therefore, lambda is equal to 2L. Okay, so plugging that in here, I have V over 2L. And that's the answer. So the answer is A. And of course, the slides explain it just the same. Okay. Standing waves in an open pipe come about as a result of A, superposition and diffraction, B, reflection and diffraction, C, reflection and superposition, or D, reflection and refraction? Well, right off the top, there are two words there that you haven't learned, diffraction and refraction. Those are words that you're going to learn about in grade 12, especially refraction. Diffraction, we can learn about it this year. I mean, it's not a big secret. Diffraction just means that a wave travels around a corner, or it can bend. Okay, so it doesn't necessarily have to travel straight, it can curve around corners. So if you're speaking in one room and your parent or your sibling can hear you in the next room, that's because your sound is curving around the door. It doesn't just travel straight. But anyways, you wouldn't have had to know that to answer this. Okay, if we have standing waves in an open pipe, what are they a result of? Well, remember that standing waves are a result of the superposition of traveling waves. So I know I need superposition, and that only appears in two of the answers. Okay? You don't need the waves to bend in order for there to be a standing wave. You need them to reflect. You have an incoming wave, hits a fixed boundary, it inverts as it reflects. And so, like I said, you didn't even need to know what diffraction means. You can simply say that C is the correct answer because this is exactly the way we learned it. Okay. Next, for a standing wave, all the particles between two successive nodes have the same A, amplitude only, B, frequency only, C, amplitude and frequency, or D, frequency and energy. Okay, so we're talking about a standing wave, so that would be the red one that's oscillating up and down. Well, if you have two successive nodes, we can't really say that they have the same amplitude. Okay, their displacement is zero, but the amplitude of the wave is from equilibrium to the point of maximum displacement. And by definition, the node will always have a displacement of zero, and it stays like that the entire time the standing wave is moving. The frequency, on the other hand, is what is only generated by the source. So therefore, it doesn't matter which particles you're looking at in the wave, they have to have the same frequency. Okay. Now, what about energy? They can't have the same energy if the particle at the node is not moving. That means there's no kinetic energy. V equals 0. On the other hand, the particles at the antinodes have the maximum kinetic energy. So therefore, that can also not be true. So the answer here has to be B. All right, here we go. This question is about waves and wave properties. Part A, Part I. Describe what is meant by a continuous traveling wave. So there's two main parts to this. You have continuous and you have traveling wave. Okay, continuous means it should not be broken up. Okay, so energy is not interrupted. That covers the fact that it's continuous and it's a wave. Traveling wave means the medium itself does not travel with the wave disturbance. And that's always the case. The medium should not travel. Part 2. With reference to your answer in AI, state what is meant by the speed of a traveling wave. Okay, well, the speed of a traveling wave, it depends what you consider to be the front of the wave. If you call it the wavefront, then that could be the speed that the wavefront is propagating through space. There's a couple ways we can define the speed of a traveling wave. Okay, so the speed at which the wave disturbance propagates, the speed at which the wavefront travels, or the speed at which energy is transferred. All of those work. Part B, Part I, define for a wave the frequency. So we saw this in section 4.2. Frequency is the number of cycles of a wave per second. It's the reciprocal of the period. Now, there is a note here for IB students, so if you use particular units in a definition, there will be a loss of marks. So for example, in reality, this is not the best definition. Frequency is the number of vibrations per second. And so it depends. Frequency is really defined as the number of vibrations per unit time. So this applies for the non-IB students just as it does for the IB students. You don't want to be too specific in your definitions. Okay, so just as when we learn about specific heat capacity, we don't really want to express it in terms of units. Okay, it's the amount of energy required to raise the temperature of 1 unit of mass of substance by 1 unit of temperature. So that would be the best definition. Wavelength. Okay, wavelength is the distance between successive crests or troughs. We could also say it's the distance traveled by the wave in one oscillation of the source. All right, next. Which one of the following is correct for transfer of energy along a standing wave and for amplitude of vibration of the standing wave? Well, if you have a standing wave, we've already covered that it's not transferring energy. Only traveling waves transfer energy. So therefore, we already took out C and D. Okay, so those two are gone. Amplitude of vibration of the standing wave. Well, we covered this as well. The only thing that has a constant amplitude are the traveling waves. We know that a standing wave, it has a variable amplitude. When the crests of the traveling waves line up, or the incoming and reflected wave line up, you have the maximum amplitude. And when they're fully out of phase, or out of phase by half a cycle, you have zero amplitude, and possibly anything in between. That means the answer has to be B. All right, let's try this. Two pipes, P and Q, are of the same length. Pipe P is closed at one end and pipe Q is open at both ends. The fundamental frequency, first harmonic, of the closed pipe P is 220 Hz. The best estimate for the fundamental frequency of the open pipe Q is, and there we have a bunch of options. So let's go to the page and work this out. Like I said for the first question, you might have no idea how to solve this. It's okay. Okay, start by writing down what you know. Start by trying to work out whatever you can if you have no idea where to go. And hopefully the pieces fall together. Okay, so if I have no idea what to do, I would do this. I have two pipes P and Q. They have the same length. Pipe P is closed at one end, so I'm going to draw them out. Here's pipe P, and pipe Q is open at both ends. Start by drawing a picture. Now, we're talking about the fundamental frequency in both of these. So I have F1P and F1Q. Now, the fundamental frequency of the closed pipe P is 220 Hz. Remember that whenever you have an open end, it's an antinode, and whenever you have a closed end, it's a node. Since we're looking at the simplest patterns, we're going to have something that looks like this. Okay, so that would be for P. For Q, it's open at both ends, so I need an antinode at both ends. It'll look something like this. All right, next we are going to come up with expressions for the wavelength of each. And actually, while we're here, since they're both the same length, we can call that capital L. Okay, so for P, I can clearly see here that I have a quarter wavelength fitting in this pipe. So L is equal to lambda over 4. Now, specifically, this is the wavelength in pipe P, so I'm going to call this lambda P. Down here, I can see that I'm fitting half a wavelength inside this pipe. So L is equal to lambda over 2, and this is lambda Q. All right, so if you're looking at this wondering, okay, I still don't see how I'm going to work this out. Well, don't fret. The next step is still the same. We have to express the wavelength in terms of L. So lambda P, it will be 4L, lambda Q will be 2L. So we have an expression for wavelength for each one. We have an expression for frequency for one of them, and we're trying to figure out the frequency for the other. Think about what is that third variable. We have frequency, we have wavelength. What is it? The third variable that we're missing here is speed, okay, the speed of sound. And I know that the speed of sound in pipe Q and pipe P is the same. In fact, the question doesn't specifically tell you that the speed is V. I'm quickly reading over it right now just to make sure. Yeah, it doesn't tell you that. But that's something you know. You know that the speed of sound is the same in both pipes. So V1 is equal to V2. We just call it V. So why don't we say this? The speed of sound in pipe Q is equal to the speed of sound in pipe P is equal to the speed of sound in pipe Q. Now speed is also equal to F lambda. Okay, so this is going to be Fp lambda p and Fq lambda q. Now, what are we looking for here? We're looking for Fq, F1Q specifically, so we'll just stick those ones in there. Okay, so F1Q is equal to F1P lambda P over lambda Q. So F1Q is equal to F1P, that's 220 Hertz. Hertz is SI, it's the International System of Units, so I can just plug it in like that. Lambda P is 4L, lambda Q is 2L. So now I have an L on the top and L on the bottom, those cancel. 4 divided by 2 is 2. So 220 times 2 is 440. So therefore F1Q is 440 Hertz. So that is B. All right, let's go back to the slides. Next, a vibrating tuning fork is held above the top of a tube that is filled with water. The water gradually runs out of the tube until a maximum loudness of sound is heard. Remember, when the maximum loudness of sound is heard, this is when you produce a standing wave. Which of the following best shows the standing wave pattern set up in the tube at this position? Now, if you actually understand how standing waves work with closed and open ends, nodes and antinodes, you can't mess this up because there is one open end, which is the top of the tube, and you have one closed end, which is the surface of the water. And from what you've seen, whenever you have a closed end, you need to have a node. So therefore, you must have a node at the water surface. The open end must be an antinode. And the only thing here that satisfies those requirements is C. If there was another option that had an antinode on top and a node at the bottom, you would have to pick the fundamental frequency, or the shortest, simplest possible configuration that would fit in the tube, because it is filled and it's drained until a sound is heard. So that would imply that it's the first sound. Okay, so if you need to copy this down, pause the video and go ahead and write it down. Next, the diagram below, or rather to the right here, represents the fundamental first harmonic standing wave of sound inside a pipe. Which of the following correctly represents the displacement of the air at P and Q? I can't tell you how many students get this wrong. It's very easy to make a mistake here. It's very tempting to pick C as the answer, because you would look at P and say, well, that point's oscillating up and down, and Q is oscillating up and down, and clearly Q is moving more than P. And you're part right. Q is moving more than P. But there's a very important piece of information in the question, and that is that this is the standing wave of sound in a pipe. This is not a transverse wave. This is a longitudinal wave. Remember that sound is a longitudinal wave, which means the particle motions are parallel to the direction of the wave velocity. So if this wave is traveling from left to right or right to left, that means the particles, so P and Q, must also be oscillating left to right or right to left. Okay. So the idea that P is moving less than Q is correct, but we just have to understand that because it's a sound wave, it's a longitudinal wave, it's oscillating left and right. So the answer is A. Okay, next. A standing wave is established on a string between two fixed points. At the instant shown, point T is moving downwards. Which arrow gives the direction of movement of point U at this instant? Well, standing wave, you know, these nodes, they're not moving, right? So this trough here will become a crest. This crest will become a trough, right? So this point T, it should make sense to you that it's starting to move down. That means this trough is starting to move up. This crest is starting to move down. That means even this point here, because it's not at the node yet, this point is still going to want to move down. Hence, it's going to move in the direction of D. So there's the answer. All right, our last problem. The diagrams below show two standing wave patterns that are set up in a stretched string fixed at both ends. The frequency of pattern 1 is F1, and that of pattern 2 is F2. The ratio F1 to F2 is, okay, so let's go to our page here. So we're going to work this out. Again, no memorizing here. Figure it out, work it out from scratch. So we've got, all right, we've got a string, and it's vibrating either in one way or the other. So here's the fundamental, F1, and here's the next possibility. So this is the second harmonic, F2. All right. So we have to come up with a ratio of F1 over F2. Now, since they have the same length, so I'll just call that L, I'm going to come up with an expression for each of them in terms of their wavelength. So for the top one, I can clearly see that lambda 1, well, how many lambda 1s fit into L? I can see that half a wavelength is fitting. So 1/2 lambda 1 is equal to L. So therefore, lambda 1 equals 2L. For this case here, I can see that a full wavelength, lambda 2, is equal to L. Well, so that's exactly the way it is. Now, using our universal wave equation, V is equal to F lambda, I'm going to rearrange this for frequency because that's the ratio that I'm looking for. So if I rearrange this for F, I get V over lambda. So that means that F1 over F2 is going to equal V1 lambda 1 over V2 lambda 2. But remember, the speed of sound is the same whether you're looking at this case or this case. So those are gone. So that means F1 over F2 is equal to lambda 1 over lambda 2. Lambda 1 is 2L, and lambda 2 is L. Okay, so what do we get? 2L over L, we get 2. F1 over F2 equals 2. Oh my gosh, you know, I just realized I drew the wrong picture here. Okay, so that is one wavelength. I need 1.5 wavelengths. Well, for this scenario, this is the correct solution, but sorry guys, we are actually dealing with F2 that looks like this. So let me redo this. So we have our fundamental frequency. So this is F1, and this is the next frequency that we're considering. It's not the second harmonic, but it's the second one we're considering. So we'll call it F2. Okay, so I guess this is good practice for you to try your hand at these questions again. All right, so here, if we call this whole thing L, the length of the string, which is not changing, I know in the first case I still have half of the wavelength is equal to L, so lambda 1 is equal to 2L, so that didn't change. Yeah, okay. And in this case I have, let's see here, 1.5 wavelengths, so 3 over 2, lambda 2 equals to L, so that means lambda 2 equals to 2L over 3. Same solution. Okay, so I'm looking for F1 over F2. So that's V1 lambda 1 over V2 lambda 2. Speed of sound is the same, so those cancel. So we have lambda 1 over lambda 2. Lambda 1 is 2L. Lambda 2 is 2L over 3. So that's 3 times 2L over 2L. 2L's cancel, and you're left with 3. Okay. So going back to our slides, that means the answer is, hang on one second, what's going on here? Give me 1 second, guys, let me see, something's going on. It might be right in front of me and I'm just missing it. See, going back here, okay, so we have half, and you've got 1.5 here. So this is half a wavelength equal to L, so this is 2L, yep. And here I have 1.5 wavelengths, or 3 over 2 lambda is equal to L. So if we rearrange that, yeah, lambda 2 is 2L over 3. So F1 over F2 is equal to lambda 1 over lambda 2 because, oh, you know what? Gosh, what a silly error. I apologize, guys. I found my mistake. And unfortunately, it turns out I did it here too. I apologize, guys. This was the formula for frequency, so I knew something was up because the answer is not matching. F is equal to V over lambda. Let's just do that quickly. I apologize. All right, so F1 over F2 is going to be V1 over lambda 1 over V2 over lambda 2. So I have a fraction over a fraction. So a fraction divided by a fraction is the top fraction times the reciprocal of the bottom fraction. So like this. Okay, this makes a lot more sense. The speeds cancel because the speed of sound is the same. So we're left with lambda 2 over lambda 1. Okay, so now looking at our values, lambda 2 is 2L over 3. Excuse me. And lambda 1 is 2L. So then 2L over 3, so this is really 2L over 1. The 2L's cancel, and I'm left with 1 over 3. Okay, so there we go. So F1 is equal to 1/3 F2. Or actually written the other way, F1 over F2 is equal to 1 over 3. Actually, let me just move that up. Okay, and there it is. So the correct answer is A. So that is the end of video 4.5 for standing waves.